Alright, so let's go over this example of solving a first order linear homogeneous differential equation. The setting is a simple circuit with a resistor and a capacitor. Resistor has resistance R, capacitor has capacitance C, and we're going to look at a voltage source that's going to vary in time. Use Kirchhoff's loop rule and rearrange things a bit, and you'll get this differential equation. Step 1, we did this to solve the homogeneous version. It's a decaying exponential. Let me add an initial condition here. So Q of 0 is some charge on the plates. And so the method we're learning is to suppose for the non-homogeneous equation, the original one, that instead of a constant, we have some function, some unknown function, times our homogeneous solution. So we take this product and we plug it into our non-homogeneous equation, do a little bit of calculus, get some cancellations, and then we have this problem. And so what this says is that if we want to find this function a, we're going to need to integrate this stuff, dt. So to do that, we'll need some form for v. So we're going to use v naught sine of omega t. So we'll specify a function. I'm omitting any phase angle. Wouldn't really be beneficial for this problem. But we still have quite a bit we can play with later, v naught and omega. So let's go ahead and set up that integral and do it. It's a good review of things. So a of t is going to be the integral of v naught over r e to the t over rc sine of omega t dt. And this is one of those tricky integration by parts problems. So what I mean is we're going to have to do this twice to end up back to where we started. So we'll let u be v naught over r e to the t over rc, so that du is v naught over r squared c e to the t over rc dt. Didn't leave myself enough room here. dv is going to be sine of omega t dt, so that v is minus 1 over omega cosine omega t. So putting that together, right, what we have is u times v, so that's minus v naught over r omega e to the t over rc cosine omega t minus the integral of v to u. But we have another minus sign here, so it'll be positive. And v du is going to be a v naught over r squared c omega e to the t over rc cosine omega t dt. And we just do the same thing again. I'll let u be v naught over r squared c omega e to the t over rc. Then du, we'll pick up another rc from the chain rule. V naught over r cubed c squared omega e to the t over rc dt. Our choice of dv will be cosine of omega t. So v is positive 1 over omega sine omega t. Put that together, and so we still have that first term with the cosine. And now our uv is going to be a v naught. We'll have an r squared c omega squared e to the t over r. I feel like I was missing something here. What am I du up here? Oh, you know, no. I guess that's fine. Yeah, this is okay. So I get Oh, that's fine. Yeah, okay. No, we're okay. We're okay. So that's sine omega t minus, now what do we have for an integral now? Well, v du, so we have v naught over r cubed c squared omega squared e t over rc sine omega t dt. Now this is pretty much the integral we started with, right? So here's the thing. We're starting with this integral, and this is what we have for it. So we can add this to both sides, and well, let me show you. So I'm gonna, if I add this to both sides, this whole integral here, and pull out all the constants, I'll have v naught over r plus v naught over r cubed c squared omega naught, not omega naught, omega squared, times the integral that I was interested in solving to begin with. Right? And that's equal to all of this stuff right here. So that's negative v naught r omega e to the t over rc cosine omega t plus v naught r squared c omega squared e to the t over rc sine omega t. Now to make this a little simpler, what I really should have done some time ago actually is to cancel out a common factor of there's a v naught everywhere here, and what that amounts to doing is kind of pulling this out and just solving this one integral. So it would be a little easier if I had this. Should have done this a minute ago, and that would give me something like this, and then we can do a unit check. So this purple business is just the integral, looking at just the integral. We'll put that v naught over r back in a minute. So what do we have here? Whoops. 2. RC has units of seconds, and omega has units of hertz. So we have second squared times hertz squared. This is unitless. This is 1 over omega is time. So we have RC times 1 omega gives us just omega, which is 1 over omega. So the units are consistent across the board. So that's good. The integral that we wanted to solve then is equal to the reciprocal of this, right, which is going to be r squared c squared omega squared over r squared c squared omega squared plus 1. Again, this is all unitless, but not equal to 1 or anything. I mean, times all of this stuff. But we're not done yet. This is easily one of the tricky things. So what we want is the full function for q, which is a of t times e to the minus t over rc. Well, that's going to be the v naught over r. A was equal to v naught over r times the integral. And so then we put in what the integral's worth, and that's r squared c squared omega squared over r squared c squared omega squared plus 1 times all the other business. And there's a little bit of simplifying you can do. Oh, and I did forget something that I'll put back in here. I just remembered. sine omega t. Now I have to have an integration constant also. This entire thing, yeah, I'll line it in purple. This is a of t. I have to add the integration constant by hand because of this funny integration where I'm just sort of integrating in circles, and I end up back to where I started, and then I have to I'm never going to finish this integration. So I have to add an integration in here by hand, and this is really important so that when I multiply by this e to the minus t over rc, that I don't wipe out, goodness gracious, t over rc, that I don't wipe out the only exponential. If you forget this d, then what happens is when you multiply by the decaying exponential, you have no exponentials, and then you have just this simple harmonic motion, and that doesn't make any sense at all. It should tend towards simple harmonic motion, but depending on your initial condition, that won't be the case immediately. So what does this end up being? Again, we can do a little simplification. There is an omega here. So I can write v naught over r. I can cancel one of these r's actually, so let's do that. I can do that. I can cancel one of these omegas. So let's write it as v naught r c squared omega all over r squared c squared omega squared plus 1 times, let's clean this up a little bit, we'll say this is sine omega t over rc omega, that's unitless, minus cosine of omega t, that's unitless, plus d e to the minus t over rc. That's our general solution for the charge on the capacitor. Now for the initial condition, this isn't as hard as you might think. If I plug in 0 for time, the sine function goes away, the cosine doesn't, it's just a minus 1. So I get a minus v naught r c squared omega over r squared c squared omega squared plus 1 plus d. So d is just the q naught plus that. So this is it's a pretty burly solution. V naught r c squared omega over r squared c squared omega squared plus 1. Then you've got all the stuff that you had before, of course. We just need to get over to where d is and place what it is. So that would be here. We're going to have q naught plus v naught r c squared omega all over r squared c squared omega squared plus 1 times that decaying exponential. And again, quick unit check. Everything in the parentheses here is unitless. So what do we have here? The denominator is unitless. One of these RC's has inverse units of omega, so they cancel out. VC gives you charge, so that's cool. What about over here? This is the same thing as this, so this has units of charge. This has units of charge. This has no units, and this has units of charge. So everything works out. I'm going to put this in some software and show you what it looks like in the next video.